A pleasure to be here, and I'm going to try and spend about an hour talking about using AI methods for research in organization science. Just to put some scope conditions here, I will not be focusing on the study of AI as a technology or as a phenomenon that affects management, but it's really about the use of artificial intelligence technologies for the purpose of research as a research tool or as increasingly a research teammate in thinking about how to do the work we do as management researchers. It's also a very deep topic and can be taught at great length. In fact, we just completed very recently a 3-day summer camp at INSEAD, which was taught with my friends and collaborators, Viviana Fonghe, who's a professor at UCL, and Piyush Gulati, former student of mine, who's now also going to be a professor at UCL, and of course a team of LLMs. And we were teaching this 3-day camp on exactly the topic that we're talking about today. So I give you that background mainly to make the point that what we're discussing today could easily be talked about for days. And in fact, the 3 days seemed very short. So I will do my very best to try and compress the essence of what we covered in 3 days in about 90 minutes. And with apologies in advance for giving short shrift to many things. So in some sense, my ambition for the 90 minutes here is quite modest. It is to show you what is possible and then point you in directions where you could then go and explore on your own. So a lot is possible, and I'm hoping that at least some of the things I show you today will surprise you. Most things I think would have been seen by somebody. So there should be nothing that should be completely surprising to everybody. But hopefully there'll be pieces that some of you have not thought about before. And this webinar will be a stimulus to go and pursue that in some more detail. I'll also mention very quickly a number of papers that are from my own work. Some of them are already published, some are still under review or still early stage in terms of development. But rather than mention them explicitly or give you reference, I'm just going to give you a link in the chat to my Google Scholar page. So if you sort it by year, then almost all the papers in the last 1 year or the 2 years, I think, are connected in one form or the other to the use of AI, either as a research tool or as a research teammate. In one form or the other. So I hope you will find those useful as well. Okay, so in terms of agenda for today, I have really 4 things to do. I want to spend a little bit of time on how modern AI works, just to make sure that everybody is comfortable and on the same page with what this technology is really doing and how it's doing it. There shouldn't be any element of mystery by the time this is done. There'll be a lot of technical detail we'll gloss over, but the core of it, I think, can be explained very fast, and that's what I'll try. I'll then move on to thinking about its use in research. And to do that, you will find that I will go back in some sense to some very basic ideas in research methodology and the scientific method. And that might strike you as a bit anachronistic, right? Why would we do that when we're talking about AI? But in fact, I'm increasingly convinced that the more powerful these tools become, the more important it is for the humans wielding these tools to be crystal clear in their thinking about what exactly are they trying to do with these tools. Which means we should be absolutely clear at every stage in the research process. Are we trying to do induction? Are we trying to do abduction? Are we trying to do deduction? And for each of these steps, we need to have a corresponding template in our mind about what is it we want the AI to do and why. Why can't we do it ourselves? So that's the reason why I'll go back to some basic ideas in research. I'll conclude briefly by touching on a very important ethical question, which is beyond the ethics of reporting and transparency, but it's in some sense the ethics of how we pass on this profession to the next generation. So what do we do about preserving researcher skills in a world in which these technologies are moving so rapidly to do many of the things that we are currently capable of doing? So I'm actually going to show you some quite surprising use cases of these tools where they really compete neck and neck, I think, for the kind of creative thinking that you and I are used to doing. And that's just going to be a reality we have to live with. So how do we live in that reality? How do we think about the ethics of thinking about these issues, I think is very important. And of course, I do hope that we will have time for a nice engaged Q&A. So I don't intend to talk for more than an hour, and hopefully we have 30 minutes for Q&A. Sounds like a plan? All right, let's do it. Okay, so how does modern AI work? So AI, of course, as many of you know, is not a completely new field. It's been around for a long time. And just so we are talking about the same things concretely, let's make sure that we are referencing the same term. So intelligence in this talk is just flexible goal pursuit. Okay, if a system is capable of solving a problem in a flexible way, we think it's intelligent. It's a matter of degree. Some things are modestly intelligent, some things are very intelligent. So if you think about a thermostat, which is able to adjust the temperature in the room, it is somewhat flexible, right? It can adjust itself to the ambient temperature, but it's not particularly intelligent. But compare that to, let's say, a heat-seeking missile, that's a lot more intelligent. But in both cases, it is really flexible goal pursuit. And by artificial, we simply mean human created. So essentially, AI is just human created systems that demonstrate capacity for flexible problem solving. And if we accept that this is a matter of degree, then we've been living with these systems for a very, very long time. A more formal, self-conscious way of referring to it as AI came about in the 1950s. Everybody in our field knows Herbert Simon. And Herbert Simon, of course, was an extraordinary character who founded not one, but three fields, right? He kind of found one of the founders of modern cognitive science, modern computer science, and of course, our own field, organization science. And he also happened to be at this conference in Dartmouth in 1956, where AI was first discussed as a discipline. And they were very optimistic, and they felt like, AI will basically be solved in the next 12 months. Turned out they were a bit too over-optimistic. It was not solved in the next 12 months. And there were long periods of very little progress. But then there were these big punctuations, which everybody, I think, should be aware of. One was the big 1997 match between Gary Kasparov and Deep Blue, IBM's AI, in which Gary Kasparov was beaten. Then there was the 2016 match, AlphaGo, in which DeepMind, now owned by Google, was able to beat the world's leading Go player, Lee Sedol. That was 2016. And then, of course, the big moment in 2012, when ChatGPT was launched by OpenAI. So what's really different between these different technologies and what has changed over these courses of time? I think this is really the central question we want to understand. And I think a very simple way to explain what has happened is we have gone from systems like Deep Blue, in which the intelligence was essentially human, which was then codified into rules, which the machines were then able to execute at very high speed, all the way now to systems which infer the rules on their own from data. Okay, a very simple analogy to make the distinction is if you were to teach a 10-year-old child how to do long division, you would show them a set of steps and they would memorize the steps and then they can apply it to any long division problem. But imagine teaching the same child how to ride a bicycle. I can't give them explicit rules. So there are rules. There are rules of muscle memory, which have to do with weight, with motion, with friction, but I can't write them down. So they have to be inferred from the training data, which is the trial and error experience of the child trying to learn the bike. Modern AI is like that. So it's mostly about discovering patterns in data and using those patterns to make prediction. So to a first approximation, pretty much all the AI we are looking at today works like this. Okay, so if you look at these examples here, I'm sure you can guess what's coming next. So what's in the first row? The circle. What's going to come in the next row? It's a square. What's going to come in the third row? It's a circle. So how are we doing this? We're doing this because we're looking at the data on the left. This is called training data. We're finding patterns in the data and using those patterns to make a prediction. And this is pretty much it, right? All modern machine learning based AI works basically in this way. Now, of course, the patterns can be very complicated. They can be probabilistic in the sense the rule might be we get two hearts and a circle 30% of the time, and then two more hearts and then a triangle 70% of the time. Or it could be even more complicated than that. But as long as there is a robust pattern which is stationary in the data, the algorithms today can find it. And there are variants of this which you would have come across probably. You would have heard of unsupervised learning, supervised learning, reinforcement learning. And they do have slightly different mathematical expressions. But at the core, they are all about pattern recognition. So unsupervised learning is like clustering. So we're trying to say if x1 and x2 go together, x3 and x4 go together, then what's the cluster into which I would place xn? Forecasting is like classic regression. So I see x1, y1, x2, y2, I have xn, what will be yn? And adaptation or reinforcement learning is I do x1, I get an outcome f1. If I do x2, I get an outcome f2. So what action should I do to get the best possible outcome? right? These are all different forms of machine learning, but what is common to all of them is they all rely on past data to learn the pattern from that data and use that to make a prediction. So this is pretty much driving everything that's going on today in AI. Now, how is this different from deep learning? You must have heard the expression deep learning, and this is driving a lot of the current use case applications. At its core, it's not that different. Okay, so maybe an analogy which everybody is familiar with will help to see that. Here's a data set in which the y-axis is intent to quit. So these are, imagine people in a company are being surveyed on a 1 to 5 scale. What's the intention you have to quit this company in the next 12 months? Confidential, okay? And the x-axis could be, let's say it's the commute distance. So just looking at this data, you can see there's a pattern, okay? And one way in which classical machine learning would fit this pattern is just by fitting a line. So in fact, simple linear regression is a kind of machine learning. If you go and take the most popular machine learning class on Coursera, it's by Huang. It's called Introduction to Machine Learning. The first 4 weeks is just linear regression. And people are often confused. I mean, we were doing linear regression. Why is this now suddenly called AI? And the answer is it's a change in what we do with the data. So linear regression, we are asking the question, what's the slope of the line? And we have a hypothesis about it, right? With machine learning, we don't care about the slope. We simply say, I have some data linking X and Y. Build me a model so that when you give me a new value of X, it can predict what the Y value will be. And it turns out the same model can do both. We can look at the slope, or we can use it as a predictive model to say, give me a new value of X. I can plug it into this and tell you what the new value of Y is. And this is an important but subtle point to bear in mind. I could give you a new value of X, which is not in the data. Right? So nobody in the data set may have exactly the new value of X that I plug in. And still the line gives me a prediction because it can interpolate. I can also give it a value of X which is larger than any of the X values in the data, and it can extrapolate. So in this sense, these models can give us back predictions which are not already in the data. So this question that comes up quite a lot with modern AI techniques like ChatGPT or large language models is, are they just repeating what they memorized? And the answer is no. Every single word coming out of ChatGPT had to have been fed in, but not every single sequence of words was fed in. It is in fact interpolating and extrapolating. And that's the reason why, to some degree, we can say they are creative. To the extent that we define creative as novelty produced by recombination, they are creative. Okay. Are they as creative as Shakespeare? Probably not, but then nor are you and I, right? So this is a matter of degree. So essentially, that's what these things are doing. Now, what deep learning is doing is basically allowing for more complicated models to be built on the same data. So instead of a line, you can build a curve. That's basically it, right? So the rest of the details about neurons and layers and all of that is technical detail, which we can completely skip if you're interested in how to use it. What matters is you can fit a nonlinear regression. And when you fit a nonlinear regression, a few things become obvious what will happen, right? One, your R square will go up because you can really fit every data point if you like. Second, you are now at enormous risk of overfitting your data. This is a problem we all know. When we put in more and more variables into a regression, R square goes up, but you also end up at the risk of overfitting the data. Why is that a problem? Because ultimately we care about predicting out of sample, not in the data we have, but the new values of X we will get for which we want to predict the Y. So the big risk with deep learning is overfitting. That's the first big risk. And the second big risk is it gets harder to interpret. So if you look at the line, I can explain it in English. I can say when commute distance goes up, the intention to quit goes up. But suppose I had to explain the curve. I would be struggling, right? And I have to say something like when the commute distance goes up, initially the intent to quit goes down, but then it goes up again, then it goes down again. And this is just one variable. Imagine doing this with 100 variables. So imagine this very complex polynomial, which is in n-dimensional space where I'm trying to fit this data, which has very good R square, but I cannot explain it in English. And that's why people say deep learning is a black box. There's nothing magical or mysterious going on. It's just a very complicated polynomial which we cannot express in English. It's actually a compound function because of the way neural networks work, but we can skip the technical detail. The gist of it is it's nonlinear regression. Okay, so how do we solve the overfitting problem? This is one of the big breakthroughs in deep learning, which is if you have enough data, you can do something quite clever. You can take random slices of your data and fit the model in some part of it, and then use that remaining part of your data to test how good is your model. So this is called training versus test or out of sample prediction. And it's a very powerful idea, which is actually quite related to something in philosophy of science as well, which is you never use the same data to both construct your theory and test it. Right? Or to put it very plainly, please don't p-hack. It's the same idea, right? One does not use the same data to form a conjecture about what's happening in the data and to test it. You can't do it. It's just circular reasoning. And this is the same point about overfitting. So if you split your data and use some parts to build the model and other parts to validate it, then you can do this thousands of times and refine your model until you're sure it's not overfitting. So that's really been the power of deep learning. So if somebody were to ask you what is deep learning, I think you can very accurately say it's nonlinear regression with techniques to control overfitting. That's it. All the rest about the neurons and the layers and all of that is stuff that we can comfortably black box for the purposes of using the technology, not for the purposes of developing it, obviously. Okay. Last but not the least, how is ChatGPT different? So you're thinking at this point, okay, this is all fine. We're talking about patterns in data. But ChatGPT seems to be different, right? And large language models are working with words, not with numbers. Is it really different? The answer is actually it's not. To a first approximation, what ChatGPT is doing is very similar. So you're putting in some words, and the model is using the structure of the model to predict what is the next most useful word to appear in the sequence. Then it's taking your word plus the words it predicted and fitting them back into the model, deriving the next prediction, and doing that iteratively again and again. So it's predicting one token at a time, one word at a time, and that's how it's coming up with results. So it really is the same thing. It's looking for patterns in the data and using those patterns to make a prediction. However, there is a very big technological breakthrough behind ChatGPT. There are two, in fact, and I want to make sure we are all familiar with them at least, because they do matter for our using these models as researchers. The first is, in this example, which is about intent to quit and commute distance, we can intuitively see that these are two numbers. So if I draw a graph between X and Y, it's clear. This is a number, I can draw a line. What does it mean to plot words in a space? Okay, that seems completely different. So how do I go from words to numbers? Because what ChatGPT is predicting is words. It's not predicting numbers, right? Actually, no. What all these models are doing in the end is predicting numbers. The trick lies in converting words to numbers. And the big breakthrough that happened that allowed us to do it came around 2013 or 14, and it was called word embedding. So word embedding is a very powerful technique that allows us to convert words into numbers. And in particular, the kind of numbers we convert them are called vectors. So they have multiple dimensions. So a very famous example to make this point has to do with this one. So here you have two dimensions. On the x-axis, we have gender, which goes from male to female, left to right. On the y-axis, we have seniority, hierarchy, okay? And what I've plotted here, since I'm sitting here in London, is a bunch of titles from royalty. So we have the king, the queen, the prince, princess, duke, duchess, earl, countess. And I've plotted them here, and hopefully you can see why they intuitively belong in the place they do. Okay, so I'm not saying that the exact location is precise, but the relative location is meaningful. So obviously the king is more senior than a prince, who's more senior than an earl. Okay, duke is more senior than an earl as well. Countess, duchess, princess, queen, these are all more female than the king and the prince and the duke and the earl. Now, why is this important? Once you've found a way to represent these words in this space, then each word can be converted into a number. And that number is simply a vector, which is the x and y coordinates. So once we have them as a vector, we can do all kinds of algebra on them. In fact, we can subtract things from each other. So in this picture, for example, if I subtracted femaleness from queen, I would get king. Okay, so if I subtracted seniority from king and added femaleness, I would get princess. So as you can see, once we place these words in a space, we can actually do algebra on them. And then it really becomes the same problem as this one. So at its core, this is what modern AI is doing. Okay, modern AI is essentially a way of learning rules from data. All data are numbers to a machine, as long as we have clever ways of converting words and sounds and images into numbers, and there are patterns in those, the machines can find them. And this is a pretty big philosophical discovery, if you like, that even the patterns you and I can't see, the machines can. In fact, there's a theorem called the universal approximation theorem, which says that if there is a pattern in a data set, there will be a deep learning algorithm that can find it, which can't be beaten. That's the precise statement, right? That there will be a deep learning algorithm which can't be improved on in terms of extracting accurately that pattern in the data. So just think about how powerful that statement is, because it says for every data set with a pattern in it, there will be a deep learning model that can find it. And not only that, you won't be able to beat it. It will be the best possible model there is. Now, the theorem doesn't guarantee that the humans will find that deep learning algorithm. It takes a lot of engineering to find that, right? That's the reason why the transformer was only discovered in 2017 and embedding only came up in 2012 or so. But it tells us that mathematically there is a guarantee that as long as there is a pattern in the data, there will be an algorithm that can find it and no human mind can improve on it. Maybe it's as good, but it can't be better. So that's a very profound insight, if you like, about what is possible with data. And that's probably where I think the current state of the art rests in terms of where the field is. So very briefly, to summarize what I've said so far, the three big changes that have happened in the world of AI are going from rule-based AI to machine learning. And rule-based AI was humans would come up with the rules based on their understanding of the problem. They would program them in, the machine would execute. That's how IBM's Deep Blue won against Kasparov. But then machine learning, the rules are not fed in by the human. They're extracted by the algorithm from the data by looking at lots of patterns in the data. Deep learning is just a particular kind of machine learning where the model can be highly nonlinear. And Gen AI is just a particular kind of deep learning which can extend the logic of finding patterns in data to words and to images and to sounds. Okay, let me stop there and see if there are any questions first to address. Ibrahim, if you could flag anything that came up.
Yeah, if you have any questions, just please feel free to raise your virtual hand so we can see you. Visa, do you want to go ahead?
Yeah, thank you, Professor Phanish, for this very interesting explanation. I just had a question regarding the, what was it, the a universal approximation theory. Now, isn't it ironic that it's humans who are coming up with the deep learning model, basically, and then we are saying that, and still the deep learning model would be the one to beat humans at pattern recognition. I just wanted to understand. And there is a contradiction is what I felt. I mean, maybe it's...
Not necessarily. I mean, it is basically the human's capacity to recognize that there can exist deep learning architectures which can extract any pattern out of data, right? So it's a bit like our being able to recognize that we can build a crane that can lift 1,000 tons.
Right.
It doesn't mean we have to be able to lift 1,000 tons, right? So we can recognize the limits of our capacity while at the same time understanding that there are architectures that can exceed our capacity.
Okay. Thank you. Thanks a lot.
Amin, please go ahead. We don't hear you, Amin.
Sorry. Do you hear me?
Yeah, now I hear you.
Yes, sorry. Just wanted to tell you that we talk a lot about AI, deep learning, everything. Before it was called neural network, you know what I mean? And I believe that it will never help us to understand what is human intuition. And it will never help us to make a decision, because decisions are made as well by emotion. AI, they will never beat human people. It will be good when we've got like a rational thinking, like when I say, you know, I don't want to talk about statistics, because for me, having an engineering background in applied mathematics, for me, statistic, it is a tool, okay, to predict, but it's not mathematics, it's not rational. You know what I mean? And it could be as well biased for many things. When you use AI example in North America, You ask him the same thing in Africa or in India, it will provide you a different response. I will not say that one time, because as well how we use the technology, because this technology is learning with our perception and our ontology and things like that. So it is good to use these kind of things, but we have to be careful to the people, you know, to the leader, how they're gonna use it, because we can use it and think that all the response, if you don't know how to use the prompt, they will provide you the truth. And sometimes the truth, you know, it's philosophical stuff. But anyway, it is what I wanted to add. Thank you anyway.
Thank you, Amin. There's no doubt that at this point, there is no argument whatsoever that these technologies are neither infallible nor globally superior to humans in everything, right? That is absolutely clear. So they make mistakes all the time. They hallucinate. We'll talk about how to deal with that as well. And the universal approximation theorem, as I said, is a claim that there exists such a deep learning algorithm. It doesn't say it can be found easily. So often we haven't found it yet, right? So there is still a long way to go before we should be worried that they can do everything we are doing and better. I don't think we are there yet. And maybe we'll never be there. Personally, I'm not sure. I feel confident to say never, but I'm certainly confident it's not today. Okay, so there's no doubt about it. Yeah, Ravi.
This is more a comment from you. You have an excellent example, you know, that logic, you remove the gender and then you can guess what the forecast is. What I think is AI has this democratizing impact. Smart people come up with the human logic, which is not prevalent among the majority of the people. For example, Phanish Puranam, who is expert in our group, may come up with a nice logic that we all cannot come up with, and then he puts it into an algorithm, and rest of us can use that blindly and benefit from his knowledge by implementing his knowledge without even knowing the mechanics of that. So I don't think AI is really smarter than humans. It is just that AI represents the best of minds in each realm of knowledge. And that's being shared across the whole globe. So there's a democratizing impact. It's not a relative expertness, AI versus humans. AI is all humans, except that AI is extra smart humans who are developing the algorithms, and the algorithms are delivering that knowledge to the rest of the population out there. That's just a comment. Yeah.
It certainly can serve the role of, if you like, acting as a delivery mechanism for one person's thinking. But I also think it would be a mistake to think that today's AI technologies are not capable of coming up with things that not even the best human expert can. We already have proof in several domains where they do it, right? So the question now is how widespread will that be and how frequent will that be? We don't know. That's an empirical question. But it would not be accurate to say that all they do is reproduce the wisdom of the best human. They certainly help with that, but that's not the only thing they do. Ibrahim, if it's okay, I move on and have people put their comments in the text chat. We can come back to it later because I do want to make sure I cover some of the content that I have in mind. All right, let's turn, as I said, to thinking about now how do we apply this very exciting technology with all its potential and pitfalls, as you already started hearing, to what we do, which is research and management. And I want to remind us all that ultimately the scientific approach we take to doing research in social science, as in natural science, is anchored with one simple premise. The goal of the method is to discover the causal mechanisms that underlie phenomena of interest. This is Bertrand Russell's classic definition, right? And this is very much what we teach in our PhD courses and what I was taught and what we teach our PhD students going forward. So this realist ontology, I think, is at the core of the way I think about research for sure, and certainly how I think about bringing AI to bear on the work I do. So it's my view. It's certainly a view I think many share, but it may not be universal. So at least I want to acknowledge this is explicitly the way I think about our goal when we do research, which is we look at phenomena, whether it's phenomena in the natural sciences or social sciences, doesn't really matter. Our objective is to try to understand what is causing. And we try to capture our account of that causation through things we call theories. And we think those theories are good when they're not just internally consistent, but they can also predict what will happen in new data sets, right? That's very much the objective for what we're doing. And if you think about Russell's explanation of it or the way I just explained it, it has certain core steps involved. I'm just quoting now exactly from Russell's classic description. In arriving at a scientific law, he says, there are three main stages. The first consists in observing significant facts. The second, in arriving at a hypothesis which, if true, would account for these facts. And the third, in deducing from this hypothesis consequences which can be tested by observation. This is the cleanest and most elegant way I have yet seen of explaining the difference between induction, which is the first step, abduction, which is constructing hypotheses which, if true, would explain the facts, and deduction, which is given the hypothesis, what additional predictions can we make from the hypothesis which could be tested in out-of-sample data, right? And these very, careful to point out that even if our deduction and the predictions are borne out in data, the hypothesis is only provisionally accepted as true, because it's entirely possible a new test might falsify it. So this is very much the spirit, I think, of what Karl Popper then extended as well. And I would say very much the spirit of what most of us teach and do when we do research. Now, why is this important to revise briefly? Because effectively AI can help us with each of these steps. Okay, so this is a busy table, but I will try and walk you through it step by step. So if you see here, the rows are exactly set up to capture those three stages that Russell talks about. There's induction, which is robust pattern detection. And by robust, I mean, we can be pretty confident that the pattern we are seeing is not noise, is not sampling error. So robust pattern detection is simply induction. Okay, roughly speaking, you can say, I see 20 black crows, and I make the induction that all crows are black. Okay, it's an induction. We have not seen every crow in the world, but we are making a statistical generalization based on the data. And our hope is we were not unlucky to see a sample of atypical black crows. That's induction. Then there's an abduction, which is the question of why. Why is it that all crows are black? And one might have different theories about it. One might say God made them black, or one might say natural selection made them black, and one might say something about genetics interacting with environment and so on. You have different explanations for why. And then you might have a deduction saying if it was natural selection, we would expect the following additional implications, right? If crows were black for the following reasons, you might also expect the same process that made them black also produce the following additional effects. Maybe their feet should be like this, their wingspan should be like that. They should have a maturation period of 2 weeks or 2 months. I don't know, I'm not a biologist, but you get what I'm saying. These are deductions one can derive from that theory. So that's induction, abduction, and deduction. And in our world, this corresponds very closely to detecting the patterns, coming up with hypotheses, and then deriving additional implications that we can test using new data. And if you think about what the researcher's tasks are in each of these stages, so with induction, we are thinking about what's the set of things we should measure, what kind of patterns should we see, how do we even conceptualize the variables. There's a step which often comes before that, which is what is worth measuring, and this is where literature reviews come in. There's the abduction part, which is constructing a theory or an explanation to explain what is going on. And there's the deduction part, which is what are the logical predictions we can make from our hypothesis. How do we set up the right experimental test if we can run experiments? If we can't, how do we test it in naturally occurring data? If the naturally occurring data allows us, can we bring it close to a natural experiment by using things like fixed effects, matching, difference in differences, instrumental variables? All of those are techniques to try and bring us closer to a perfect experiment. We can't usually do it all the time. But that's what the deduction part is. And if you think about where AI can be used in each of these steps, it's helpful to separate machine learning from generative AI. So what machine learning can help us with in induction is robust pattern detection. Okay, so it's kind of surprising for people that we can do induction with large sample data. Most people seem to think inductive work is only qualitative, but that's not true. In fact, we suspect very often people are doing a lot of induction in large sample work. They're just not telling us, right? They might be writing it up in a way which makes it look like it was all deduction. The reality is, if you are looking at a large data set, of course, you will test your first hypothesis, but you're not going to stop there. You're going to explore and look for what else is going on. And I think that's good science, as long as we are transparent about it. If we are not, then it becomes very bad science and fails to replicate, right? So it's a subtle but important distinction. And machine learning can be really very powerful with this, because it can help us detect robust patterns in a way that running regressions and seeing what comes out to be significant cannot. Okay, looking for low p-value variables is a very poor way to do pattern detection. So stepwise regression, which used to be the standard data science technique 20 years back, is being thoroughly discredited now because it's very, very prone to turning up false positives. What machine learning can do, which is much more powerful, is split the data into subsamples and see if you get the same robust pattern in different subsamples. That's the first important thing it can do. The second thing it can do is it can also help you choose how complex or simple do you want the pattern to be. So I could choose to have a very high R-square model in which I have third-order interaction terms. But good luck trying to explain that theoretically. Or I could say, you know what, I'm willing to give up my R-square. I'm willing to go down from 90 to 70%, but scale down the interactions from third order to second order. So I can make an informed choice about the difference and the trade-off I'm making between explanatory power and explanation. And I can do this in a calibrated, fully documented, reproducible way. So this is what machine learning allows us to do. So that's algorithmic induction. It's been extremely powerful in text analytics. So to measure constructs from text data, I think machine learning has no equal today. Okay, the degree of reliability and reproducibility we can get far exceeds what human coders can do. There are multiple studies showing that now. So if you want to really look at large samples of text data and aggregate them up in a way that others can easily reproduce with high reliability, machine learning is the way to go. Abduction, which is the construction of patterns, the construction of explanations for patterns, machine learning traditionally could not do. In fact, we wrote a paper in 2020, which is about algorithmic induction, where we stated quite boldly that the construction of theory to explain patterns still remains a human prerogative. Okay, that was 2020. By 2022, we had to revise our argument. It's no longer true. So GenAI can come up with very credible counter explanations for robust patterns in data. Okay, in fact, I'm going to show you an application that does that. One of the most useful ways I've used this now is to come up with alternative explanations for my results. Why should I wait for the review process and some annoying reviewer to come up with 3 alternative explanations? I can do it myself, right? Using the GenAI tools in my hardware. And finally, in terms of causal inference, we can use machine learning to do improved matching, for example, improved construction of counterfactuals. So this could be synthetic controls, for example. We can do regularization or control variable selection. It's called double regularization. So these are all pretty standard econometric techniques now with machine learning, all of which help us to improve the quality of our standard econometrics. Okay, so each of these have probably a dozen papers on them now, and I can give you references if you like. So that's all traditional machine learning. But I think the really big revolution now is with generative AI, because everything in the third column, which required coding, could now be done conversationally. So a big part of what we did in the 3-day workshop at INSEAD a couple of weeks ago was showing people how to produce the code to do this analysis without having to write a single line of code yourself. This is now possible, right? And it's actually inbuilt into code editors like Google Colab. So if you can think clearly and state down the steps needed, you can write it down in English and Google will produce the code in Python or in R, whichever language you like, which you can then compile, document, and share. And that's quite an eye-opener if you haven't done this before. So I would strongly recommend trying it out if you haven't. Even if you've never coded before, you should be able to produce workable code. For somebody like me who has coded a lot, I find this a very useful time saver for me. So if I know exactly what I want, I can describe what I want, and the machine will write the code. I can quickly eyeball it and check if it makes sense, and I can run it, and that's it. It's extremely well documented. It's reproducible by anybody, and I can save and share that. So that's like a very powerful general purpose application of generative AI. But the really interesting thing is you can actually use it as a theorist. So just like human theorists come up with explanations for empirical pattern, we can use GenAI to help us in suggesting alternative explanations for the empirical patterns you see. And it can also critique your own theory. So one exercise I want to very briefly mention to you, which we did in our workshop, was a lot of fun. So there's a paper in SMJ which came out recently, which showed this very interesting pattern. The pattern is when restaurants receive a food quality award, within 6 months, their risk of going bankrupt increases. So think about that, right? So you're a restaurant owner, you think you've succeeded, you won a prize, and it turns out your odds of going bankrupt actually increase. So why would this be the case? And the authors did a fantastic job of laying out all the possible explanations here. So this is not in the training data for GPT-4 because the paper came out recently. But we could show that we can ask GPT-4 the same question with a little bit of pre-prompting. So I will show you what we set up for it in a second. But if you teach GPT-4 some basics of how to think using causal graphs, how to draw causal diagrams where you have X going to Y, mediators, moderators, all of that stuff, it can come up with a number of very interesting alternative explanations. So for instance, it can come up with the explanation that when the restaurant receives a prize, customers' expectations skyrocket. And because their aspirations for the quality of food they want to eat are so high, anything the restaurant serves up disappoints. Right? So that's one of the reasons why they might go bankrupt. Another is that the suppliers can see the success of this restaurant and they start gouging them. They start extracting rents from them. Okay. A third might be the price is actually recognizing that these restaurants have over-invested in quality. So in fact, the price is just an early indicator of the fact that the restaurant is going to fail anyway, simply because the restaurant is over-investing in quality. These are three completely different explanations. Okay. And the authors, full credit to them, have thought about all three and have ruled them out. But what I wanted to point out is this sort of thinking is now within the grasp of large language models. They can do it too. Okay. And finally, of course, in deduction, you can do measuring and testing. We've been using these LLM models to help us design experiments. So recently we were running some experiments in China in a hospital about how to use AI techniques to improve the training of young doctors. So it's a real challenge in cancer diagnosis in China that it's a large country, lots of people have cancer, not enough doctors. So we could give them AI tools that would make their productivity go up. But the risk is they may be able to generate many more diagnoses, but in doing so, they may lose the skill of being able to diagnose on their own. So how should we use the AI in such a way that they deliver more diagnoses, but still retain crucial skills, which help them as a doctor doing other stuff, right? This is like a foundation skill. And we were thinking about what is the best way to design experiments to do this. And partly we were relying on the LLMs prompted by us to come up with an army of possible designs. And they could, and we could think through that space of designs and narrow down the ones that really made sense. And we just completed running the field experiments last month. So effectively, there is a role for these tools, not just as traditional design tools or research methodology tools, but increasingly as teammates. And I think that makes them both very exciting, but possibly also a little unnerving. Okay? Because this raises the question, what is our unique advantage when we do this? So all of this, I think, is quite new. The use of these techniques for pattern detection was old, but everything in the last column, I think, is potentially new. I want to talk about text analysis in a bit more detail because I feel for many of you, this might be the first use case that you will use machine learning and AI for. I think it's helpful to bear in mind that we can do broadly 4 things with text with machine learning. The first is simply counting things up. Okay, we can search for the known. So we can build a dictionary of words, including sentiment words. This is how Leak works, or senti-strength works like that. And it can simply do a frequency distribution of words connected with different sentiments. And that's pretty powerful, right? You can do that with text and compare different texts and see which ones have what sentiment. But the much more powerful use case is where you can extract key themes. And this is called topic modeling. So topic modeling is the extraction of key themes from large bodies of text. It's a very robust technique now in machine learning, and it uses typically a method called LDA, or latent Dirichlet allocation. There's some technicality behind how that's done. I can refer you to a paper in a second. But effectively what it's doing is what you would do when you were trying to extract key themes. You would read the documents again and again until you started seeing commonalities. In this case, the commonality is co-occurrence of words. So it looks for these clusters of words that are co-occurring again and again and uses them to construct key themes. A third way we can use words is to measure distance between what people are saying. Okay, so that's a very interesting difference compared to the first two. The first one is just counting up frequency of words. Second is what are the key themes. But a third kind of use case might be, I said something, you said something. How similar is what we said versus how different is what we said? And this is based on measuring distance between our language. And how do we measure distance between our words? By using embed. Right? Back to my example of the king and the queen and the princess. So once we find a space to put these words in, we can measure the distance between words by treating those words as vectors. So we can compute cosine similarity or something like that, which will tell us how close and how different these words are from each other. So that's again a very common use case. So we can measure, for example, how similar are two patents? How similar are two papers? How similar is the annual statement by the CEO of a company compared to the CEO of a rival company? Okay, these are all things we can do once we can measure these distances between text. And now, of course, we have the transformer, which is the large language model architecture, which combines embedding plus transformer to produce generation. So we can actually generate entirely new text. So there are a number of papers now in this space, which I'm happy to pass on to Ibrat. He can give you a reading list if you like. But I'll briefly point you to a few that I know very well because I wrote some of them. So this is a paper in which we measured the strength of organizational culture using text. So this came out in Humanities and Social Sciences Communication about 3 years ago. What we did was we got hold of the entire data set from Glassdoor of employee reviews. So that's about 6 or 7 million reviews from 400,000 companies. So these are very brief statements where employees say, this is what I like about my company, this is what I don't like about my company. And using that, we are able to construct the key themes that emerge within each company, unique to that company. Now, the core idea here is this. If you see two companies, and in one company, people all talk about the same few things when describing what they like about the company, we think of that as a strong culture. In contrast, in another company, if people are all over the place, they're talking about many, many different things, we think of that as a weak culture. So this was our operationalization of culture using the construct of cross entropy, which is really a technical way of measuring the strength of that distribution. And then correlating that to a variety of measures that prior literature has suggested are connected to culture. So if you're looking for a way of using text to measure the distribution of mind share of those who wrote the text, this paper could be helpful because it basically does exactly that for the case of culture. Another paper by my friends Amir and Samir Srivastava, Amir Goldberg and Samir Srivastava that I would point to. This is a very good use case for using text to measure distance. Right? So we measured key themes, they're using it to measure distance. And their paper looks at using word embedding to find out where do the newest ideas actually emerge from in social networks. And their finding is in the title. It says a deep learning model of prescient ideas, ideas which are ahead of their time, demonstrates that they emerge from the periphery of the network. So the most radical, far-reaching ideas seem to come from not the core, but the periphery of the network of scientists and reporters and authors. Right? And this is based on distance measurement using word embedding. So this is a different approach to using text compared to ours, which is topic mining. We formalized this approach of using data to do induction in this paper called Algorithm-Supported Induction to Build Theory. Came out in 2020. Seems like a long time ago now. But this is really the idea that you can use big data to do induction. And the way to do it without succumbing to p-hacking or hacking is to be very transparent about what you're doing. That's obviously step one. But also to separate your data into two parts. So the two core ideas in this paper, which had never been put together before, I think, was first the idea that you can take a large data set and randomly split it and use one part for doing pattern detection, building your theory, and then using the other part for testing your theory. So what you're really trying to do is replicate the logic of replication. It's as if you ran two studies, not one, right? You took two random samples from the population. Ideally, these would be independent. These are not. So this is not the first best. The first best would be two completely independent random samples from the same population. But this is at least two random splits of the same single sample. So it gets us close, but not perfectly. And the difference vanishes with sample size. But that's only one part of it. The second novel idea in this paper is to use machine learning to fit first the most complicated model that gives you the highest R square in the training data, the first part of the data, and then tune it down to make it more and more interpretable. So the stepping down of the model complexity and giving up R square at every step in a very conscious way, I think is the other new idea in this paper. So we can construct a theory which is tunably complex from the data. We can build the most complicated model, which is high R square, and then give up R square and make it simpler and simpler till you get to a point where you say, this I understand, I can explain this. And then, of course, the real test of that is in the holdout sample, right? And we were quite careful to point out we should test for replicating the pattern, but also for what we call out-of-pattern predictions. So these are new implications of the theory you constructed in sample 1 that didn't show up in sample 1 because they may not have been the strongest correlations. But if your theory is true, they should hold, and you would test those in sample 2 as well. So all the steps in that are described in that paper. Notice in step 3, we said use human intelligence to theorize. And that was because it was 2020. There was no ChatGPT, there was no LLMs. But now we can use the power of LLMs to help us in this step as well. Okay, and I want to show you a particular custom GPT, which I make available to my students to help them in their work. Maybe you find this useful as well. So Theorista is a verbal theorizing assistant. If you have an OpenAI account, even if it's a free one, you should be able to access it. So what we've done is given it extensive documents in the background, which allow Theorista to take any verbal argument and convert it into a causal graph. So if you give like a long stretch of text, it can convert it into here are the key variables, here are the causal relationships between them. And then you can use that to analyze the theory any way you like. So I hope you will find this interesting. This is also the technology we use to come up with the alternative explanations for the restaurant example I showed you. The last and probably most current cutting-edge application of AI, generative AI, is to start using these models as, if not substitutes, but prototypes of human respondents. So this is the paper that made a lot of impact. I think it came out 2 years ago by Lisa Argyle and others. It's called Out of One, Many, using large language models to simulate human samples. So the idea is you could take demographic data about voters, for example. Are you male? Are you female? What's your ethnicity? What's your income? Where do you live? Things like that. And use that data to get the LLMs to predict how would you vote in the next election. Okay? That sounds quite far-fetched, but they did it. They could show that actually these models are not bad at predicting exactly what people would do. And this obviously spawned an entire line of work now on thinking of using these as substitutes for humans in all kinds of lab studies. So there are startup companies out there, I know, which are now using synthetic focus groups. So instead of using real humans in focus groups, we can use data from past humans in focus groups to train these models to act as synthetic focus groups. I have a startup where we are building synthetic A/B tests. So we can create panels of consumers where we can run different A/B tests, different experiments, and get a basic idea of what's the response going to be like. So one way we've done it, for instance, is to take data from Glassdoor, use that to create synthetic personalities, and then create panels of A/B testing using those synthetic personalities. And that's useful because if you want to implement some new organizational intervention, right? What do? Normally, you would implement it and hope it works. You could ask a few people and hope they like it. Or you could ask 200 AIs and run all kinds of variations on it and test and find the one that seems most likely to give you a positive signal. So that's kind of the direction where this is going. It's still not clear that these are actually good substitutes or good predictors of human behavior. In fact, there's a very active debate going on, which currently is questioning our reliance on these kind of models as substitutes for humans, and I think they're right to question it. At this moment, I think it's fair to say AIs are not a substitute for human subjects, but they're often a better forecaster of what human subjects will do than humans themselves. Okay, it's a very interesting subtle distinction. So you can't use an AI to replace a human in saying what the human would do in the lab, but the AI turns out to be not bad at predicting what humans will do in the lab, and often it can predict it better than human scientists can. So it has this very interesting use case right now of acting as, if you like, a surrogate social scientist who can give you some hunches or hypotheses that you can then use to test. So I would think about it as not a replacement for human subjects, but as a prototype. So if you're a lab experimenter, for sure, please run your first experiments using LLMs. They will iron out all the flaws in the reasoning and use it for responding to surveys, for example. I would even use it for testing your interview protocols, right? Being very clear that what you're getting from the AI is not data. It's a prototype of your research methodology, which you can then refine and improve on. So these are some of the ways we can use these techniques. I want to close with a few points about ethical use and skill preservation, and then we'll open it up to questions. So it's obvious that we have to be transparent about the use of AI, right? You must declare, I think, in any article you submit, most journals have explicit policies around this. You must declare what use you made of the LLM. You must take responsibility, right? I tell this to my MBA students. I think the same is true for us as well. Ultimately, we are responsible for the content. So if the LLM hallucinates and makes an error and we submit it, it's still our problem, right? We have to take responsibility for it. And we have to be very conscious about protecting our own skills. If we rely on these tools to the extent that we lose our own basic skills or never build them, if you're a PhD student, then we are doing ourselves a disservice. Okay, and of course, we shouldn't lose the element of fun here. Right? Partly why we do what we do is because we enjoy doing it. And if we take that element of enjoyment out and outsource it all to the AI, then I think it's a very sad future we're building for ourselves. So I think the imagery I have in mind is something like the contrast between the calculator and the abacus. Okay, an abacus, if you're familiar with it, is a way of trying to create in the physical world a way of representing place value of numbers. So tens, hundreds, thousands, millions, and so on. And its power comes from the fact that once you become very good at it, even if you take the abacus away, you have trained your mind to think in terms of place value of numbers. So you can kind of imagine how to do the math, even if you didn't have the abacus. Okay, there's evidence. This is not just my claim. There are evidence of people being able to do abacus level computation without the abacus because they can imagine it. They've been trained to think that way. Now contrast that with the calculator. So you give people a calculator, their capacity to do computation increases, but you take that away, you got nothing, right? Probably you're worse off than where you started. So we want to think about using these tools more like an abacus rather than like a calculator. We want them to be a way of upskilling ourselves rather than downskilling ourselves. And one of the most powerful ways of doing that, I think, is also the solution to hallucination. How so? How do we solve for hallucination with LLMs? Is actually the same question as how do we solve for the fallibility of humans? And the answer is we use collective wisdom. Right? One of the most important breakthroughs, I think, of our species is a trick, which is thinking with many minds. So thinking with many minds is more powerful than thinking with one mind, not just because of scale, but because of error cancellation. If you think about how committees and teams work, both work by the principle of using differences in people's thinking. So in a team, the difference shows up as specialization. In a committee, the difference shows up as error cancellation. But in both cases, it's difference, right? That's a very core idea in organization design. The differences lead to powerful outcomes, either because of specialization or error cancellation. And the same is true for LLMs too. So we have to use these as members of a team in which we are also thinking. So if we think alongside the LLM, our own capacities remain in use, and therefore we don't use them. If we outsource completely to the LLM and stop thinking, then it's like any outsourcing situation. What you outsource, eventually you lose, right? It's just like use it or lose it applied to research skills. So I think the way going forward really is to be very mindful about where are we using these LLMs, what are we using them for, and what's the implication of reliance on them for our own skills in that domain. And the answer could be different for everyone, right? So I have students who say, I've never coded. Should I learn how to code or should I start coding using an LLM? And I also have students who are saying, I want to learn how to code because I think it's going to be a strength for me. I can think very logically, I can think rigorously. And there are people who are very good at coding who say, I don't want to waste time learning some new programming language. I can code in Python. I want to be able to translate to R. Can I use an LLM? And the answer to all three students is quite different, as you can imagine. So you have to make your own personal choice about what skills are important for you, what are not, very much like a CEO does when making outsourcing decisions. And that's how you have to make a decision on where to use these techniques and where not. Let me stop there and open it up to questions. I'm sure quite a few have come up in chat. So Ibrahim, if you will guide us through the questions, then I'll be happy to try and take a short answer. Thank you.
Yeah, thank you, Phanish. If you please just raise your virtual hand so we can see you and call you if you have any questions. There were a few questions in the chat earlier from Ayuk and Mengyung.
So I can start taking them in the sequence I see them in the chat. Is that okay?
Absolutely.
Okay, so let's do that. So let me get them here. Okay, so this is from Pearl. The question is, could you elaborate on the dangers of AI? Preliminary studies have indicated the dependency on AI. So I'm assuming you've all seen the recent paper by Patty May's group at the MIT Media Labs, right, which shows that the cognitive activation as measured by fMRI studies for people who use ChatGPT can actually decline. Okay, so the experiment is very simple. They have 3 groups of students who are writing essays with and without the use of search engines and ChatGPT. And what they find is that those who use ChatGPT not only can't recall the essay they just wrote, but as much as 4 weeks later show lower mental activation in their prefrontal cortex. So that's quite worrying, okay? We've just completed a study in China where we've shown that using AI to help you do cancer diagnosis and then taking the AI away actually leaves people more competent at cancer diagnosis. So in some sense, we have the opposite result, that using the technology actually makes people smarter. So how can both be true? And I think they can, because it depends on, is the technology allowing people to offload completely, or does it force them to still think? Right? So cognitive offloadability should become a very important design feature of these technologies. So ChatGPT has very high offloadability. You can simply copy paste the output and stick it in, and you're done. So it's not surprising that Patty finds what she does. In our case, the machine doesn't give you a yes/no answer on cancer. It gives you a probability. So the human still has to convert the probability into a yes/no. And even that minimal level of thinking we are finding improves human skills. Okay, so I think this is really the idea we should all be thinking about in our own use of AI, that you don't want to be offloading, okay? Or you're offloading only for things you're absolutely sure you have no use for those skills. So it's a strategic decision just like any outsourcing decision. Hopefully that's helpful. Okay, I think with the hallucination point, I've already made the point that hallucination problems are quite significant, but they are reducing. I will point this out. So if you look at the latest models, they hallucinate less than the ones from 2 years ago. But I still feel the best way to deal with hallucination is ensemble. So ask the same model multiple times in different context windows. And if you can, ask different models the same question. Okay, so instead of relying on a single AI, use a committee of AIs and use the consensus estimate. That seems to be a reasonable way to beat hallucination. I'm just going through the text ones and then I'll open it up to the hands here. So Mengying asked, what are the 2 major breakthroughs? So one is embedding, the other is the transformer. So embedding is just a way of representing words in a high dimensional space. The transformer is a way of moving through that space to predict the next token, right? That's what allowed the ChatGPT to come up. Find it a bit challenging to disentangle various terms related to AI. Yeah, I too, me too. Could you provide a brief explanation on the interconnections between neural networks, word embedding, large language model? Look, it depends on what you want to do with this knowledge. If you really want to understand how large language models work, you need to take a week or 2 out of your life and really get through the details of the math. And I'm happy to give you the references that will help you do that, right? But if you want to be a good user, I don't think actually you need to know how a neural network works. You need to think in terms of functions. So what's a function? A function is just, a mathematical object where x goes in and y comes out. So as long as you understand the properties of this function and its weaknesses and how the function is constructed, the details of what happens inside the function can remain opaque, right? So this is a choice that you have to make. So why don't you think about that and let me know if you want to know more about resources to understand the math behind how neural networks work. There's a lot of very good material on the web. I'm happy to point you to those. And Aaron says that's how I learned to code. Exactly, right? So Aaron's use case is one where he's relying on Gen AI not to outsource the coding, but to develop his own coding skills. And I think that's a perfectly legitimate, in fact, I would say recommended approach to use this. Kate is asking, you mentioned Google Colab for vibe coding or writing down your prompts in human language. Is Visual Studio by Microsoft worse than Google Colab? I don't know, Kat, I haven't used Visual Studio. I use Google Colab for my coding. And I've often compared it with the kind of code I get just by putting it into Anthropic or into OpenAI's GPT-03 and above. Even 4.0 is okay, actually. And I think Google Colab is slightly better. So I would say Anthropic and Google Colab are neck and neck, and OpenAI is a little bit behind in terms of coding. I would mention, by the way, I'm triggered by looking into conversation between Kata and Alan, that one of the problems of using models from the state-of-the-art foundation model providers like OpenAI and Anthropic, they keep changing the underlying models without always telling us. Okay, so if you care about reproducibility, I strongly recommend also doing the same analysis using something like an open weights model, maybe like Llama or DeepSeek. Okay, so you can document that, run it locally off your machine, and then that way you can reproduce the results. The title of the OS paper, Wei Chang, if Ibrahim, if you could just post the algorithmic induction paper, that'd be helpful. Thank you. Let's see. At what point do you think use of LLM AIs will become normalized and society loses key capabilities in cognitive skill? They're two separate questions. Hopefully, normalization will occur before us all becoming dumb, but yes, they might go hand in hand. I think it's a real risk, as I acknowledged. One question. Do we have to put up with fakeness before they're corrected by collective wisdom? Yes, and I think we haven't seen the worst of fakeness, right? There's a big problem coming, which is more and more of the training data going into LLMs is LLM generated. So it's actually getting quite challenging to be able to get data into the training, which is not also produced by LLMs. And some of that LLM produced data is obviously false. So being able to curate high quality data is really going to become super important going forward. Right, so this is where companies which sit on a lot of data have a lot of advantage. And by the way, when I say data, I don't necessarily mean things in spreadsheets. For us as humans, individual life experiences are data as well. And these are unique data, right? These are unique and proprietary data. So things like that, I think, still represent quite an important source of competitive advantage. Swati's question, I think I have answered. Thank you. Novel methods. So on the use point, I think this is a very important question that Jiongni Mao is asking. Look, there is a great temptation I see in papers being submitted for review to use the most recent cutting edge shiny algorithm that somebody in computer science has come up with for doing something in NLP. I would resist the urge to adopt that for your submissions to management journals. Why am I saying that? I don't want to sound like a killjoy, right? But the point is, your reviewers may not be familiar with it. And we don't yet know all the pros and cons of these latest algorithms. If you're doing topic modeling, for instance, please show me the results with IDA. Okay, and then you can show me some more super duper latest versions. I'd be very happy to see those too. But let's be clear, our contribution, at least in management, typically is using these techniques to make insights and advances in our field of science, which is how organizations work, right? So therefore, to me, it's not so important to take the most recent advance coming out of computer science as it is to take the most robust one. So let's try and use the most robust ones as far as possible. Okay, let's turn now to questions in the room, if that's okay. I think we've had quite a few people raising hands earlier. Visa, go ahead.
Yeah, Professor, once again, thank you for that excellent presentation. I just had two practical concerns. One is, how do you protect your data from being used for training the AI model when you are kind of, using it to run tests? So that's
there are
one.
two answers to that, Visa. One is, how much faith do you have in Sam Altman?
Not very much at the moment, sorry.
Okay, good. I'm glad you say that. So because the terms of service in OpenAI actually are, if you have a paid account, they should not be using your data for retraining their models. That's what they promise.
But do they do what they say?
I don't know. So that's why I said I wanted to ask you, what is your level of trust in Sam Altman? So my view is there's nothing I'm doing that is so rocket sciencey secret that I need to protect it. So I'm willing to trust Sam Altman. Now, suppose you don't want to do that. You might say, maybe I trust Dario Amodei. So Anthropic is more trustworthy because for sure, Dario seems to be making a lot more of the correct noises about AI ethics and safety. But a third option is to use an open weights model. Okay, so if you're willing to live with a not quite cutting edge LLM, which may not be as smart as GPT-03, right? Then you can use one of the Llama latest models and then you can run it locally off your cloud infrastructure and you can be sure your data remains local. So it comes down to how do you trade off paranoia versus convenience?
Okay, that's a good way of putting it. I mean, and just one last question. As a reviewer, how do you handle the fact that, the data might be cooked up by, or the data might be entirely generated from AI? There's always that risk, right? How do you differentiate?
Oh, but we didn't need AI for cooking up data. right? As you probably have known from following all the major scandals that have happened.
Right, yeah.
Yeah. So look, there is no technology is not going to solve problems of human morality. If people want to cheat, they will cheat, and this will allow them to cheat on steroids. There's no doubt about it, right? But it's also the case that these techniques help us to detect cheating better than they could in the past. It's a kind of an arms race on both sides. So I don't think the AI technology per se makes cheating necessarily more likely. Maybe it makes it easier for some people, but if you have ethical standards, you still won't cheat. And if you do, people will also have the tools used to catch you. So I would worry less about that because I doubt most people set out in our industry to do some cheating, right? So that's less of a concern. What we can do, I think, though, and reviewers are beginning to do it, editors are beginning to do it, is they want to see the data. So at least during the review process, you might be asked to share the data in order for reviewers to replicate some of the analysis. And by looking at the distribution of data, we can usually kind of tell if there's any egregious case of manufacture of the data.
Thank you so much, Professor. Thank you.
Okay. Aminath, you want to go?
Hi, I can't seem to have turn on my video. I apologize. It says it's disabled. I had a question about something you just said about topic modeling. I'm actually using Brett's topic for my for my topic modeling. I know LDA is really popular, but for my type of data, I just couldn't justify using LDA because my data is short form data.
Okay.
And I've searched high and low, and I've not seen anybody use the topic modeling that I want to use in management journals. So how do I justify that? LDA is obviously the most popular one. And I know you're saying that means most reviewers are more comfortable with LDA, they are more knowledgeable about LDA. How would you suggest I kind of like present that to my reviewers for that?
I think actually BERT topic is perfectly sensible for short text documents. In fact, I don't think of there isn't a better way to do it, right? BERT topic is, I think, state of the art. What papers can we recommend? So I don't think it's important that you only refer to papers in management. It's important to refer to papers in social science. So as long as you can find something in sociology or political science or in marketing actually is very ahead of us in the adoption and use of these techniques. And there are plenty of papers I know off the top of my head which are using BERT topic for review data.
Yeah.
Right.
Yes.
So I think it's perfectly fine to cite those. So I think what I was warning against is picking up something from computer science, which has not yet made the
I was
crossover
worried.
into social science.
Thank you so much.
Okay. All right, Shaila.
Thank you so much for this. I actually wanted to ask you, I'm a qualitative researcher and I'm a little bit at sea as to how AI could be used in qualitative research. That was my question. Thank you.
I'm not a qualitative researcher, Shaila, so I should not be giving you advice on this because I know that in qualitative research, there are also strong views around the use of technology for doing qualitative research, which are not just tied to issues of efficiency, but are also tied to issues of identity. Okay, and I do not want to be the person to misguide you by giving you my views because my views may or may not be the right ones for you. I do recommend looking at the very nice article by my friend Beth Bechke, which came out in ASQ recently, along with Jerry Davis. I think it was in the list of pre-readings that Ebrard shared. And they have a point of view, which is really a very thoughtful one about not losing the sense of craft and community that qualitative research is as much about as it is about the science itself. So that's their point of view, right? So if you want a insider's point of view, I recommend looking at their argument.
What did you mean specifically by identity? What has that got to do with AI?
In the following sense, it is now possible for LLMs to make that crucial leap of creativity, where you go from a huge volume of text to a few categories. If you believe that that is indeed what defines a qualitative researcher, then giving that up should not be free, right? It should come at some cost. And how much cost you're willing to incur for that is really the question that you have to decide on. And I don't want to advise you. So.
Phanish, there's also a question in the chat from Darren. How much impact does AI have on publication potential? Is there stigma for using AI?
I think we are unfortunately right now at what I would describe as a hypocritic equilibrium. So many people are using it, few people are declaring it. Okay, it's only going to get worse because the functionality of the tools is just going up all the time. So I think the only way to diffuse this equilibrium is for journal editors to be really proactive in saying we encourage the fully documented and reproducible use of AI. And some journals are moving in that direction. I don't know if you have seen the recent editorial statements from Science. I think it's a step in the right direction. The SAGE journals have done the same as well. So they said, fine, you can use AI, just tell us how you did it and make it possible for others to reproduce it as well. So once we get to that, I think it will be widespread. But to be honest, even if you just cared about the science, we now have tools that improve the quality of our thinking and analysis. Why would we not use them? Of course, we should use them. So I think eventually we will end up using them more and more. But hopefully we will also develop some norms about how to declare and report them.
Hope has a hand raised. Hope.
Go for it.
Yes, in regards to the question regarding use of generative AI with qualitative, didn't you mention earlier that a person could utilize generative AI to possibly validate their interview questions or something of that nature? Was that something you mentioned?
Yes, so that's a bit different from analyzing the data. So what I meant was, let's say you're developing a protocol to interview people in the field, right? Before you actually go and test it out on any humans in the field, because interviews are expensive, right? They consume time for the interviewer, it's an opportunity cost. Suppose you want to check out whether the wording of your questions is capturing the spirit of what you want to ask. You can ask your LLM to act as a synthetic subject and respond to your questions. So you can use that as a way to sharpen your questions or improve the wording of your questions. I would not use that as data. That was the point I was trying to distinguish.
Okay. So it could be a use in terms of her qualitative question preparation.
Yeah,
for
exactly the same as you would use it to test out your survey questions or your experimental manipulation for a lab study, right? I think those are all non-controversial in my view.
Thank you.
Phanish, if I may, a question as well, building on the earlier discussion about publication. I can see how the temptation to use AI to craft whole paper can be quite high, maybe particularly for junior scholars who find it difficult. Maybe they haven't quite mastered the craft of that. And I'm hearing more and more, people saying that papers that land on their desk for reviews, they feel there was a use of AI. What are your 2 cents in terms of what might be the potential impact of using AI for our profession in that respect?
On the positive side, I feel like if used smartly, these tools can really improve the quality of our theorizing, our analysis, and the reproducibility of our analysis. Right? So for instance, if I were to use a tool like Theorista, which I shared with you, I think it actually expands the possible explanations for data that I would be able to construct. So it is improving the quality of my thinking. If I use it to document the code I use and the analysis I do and write good notes so that others can reproduce it, this is an improvement in the science. So I think that's a positive. The downside I see is if we rely to the extent of outsourcing a lot of our thinking on it, then it weakens my own capacity for independent thought. Right? So in a different project, which you can also find on my SSRN page, we make this distinction between losing skills and losing meta skills. So losing skills when technology changes is commonplace, happens all the time, right? We've all lost the skill of how to do laundry by hand if you're using a machine, but nobody's complaining, okay? But losing meta skills is a completely different game because these are the skills you need to acquire new skills. So higher order cognition like problem solving, creative problem formulation, counterfactual thinking. If you become over dependent on these techniques, these technologies for those kind of cognitions, it's a problem. The temptation, as you correctly point out, is for younger people to go with the over-reliance model because it's productive in the short term, right? But hopefully we are, through workshops like this, putting the idea out that you're in this for the long game, right? Not just because tenure takes 7 years, but most of us have made a commitment to be in this profession because we enjoy doing what we're doing. So if you care about being a good scientist, then why would you handicap the most important skill you have, which is your capacity to think? So if that message gets through, I think people will, I hope, learn not to overuse these techniques. That's the hope. Let's see.